Hello, everyone. Welcome back from your spring break. I trust that you had a good break. Today, we're going to be starting on the second half of the semester. We're moving away from cabling and wiring techniques and moving into our individual electronic components. The end of this semester, remember, we're going to be building our guitar pedals. And so we need to be able to identify all the individual components that go into those. And of course, we're also approaching this from the perspective of doing repairs and maintenance. So all of these components we're going to cover by the time we get there. You're going to understand what they look like, the general idea of what they do, and how they fit into a document like this. So this is a schematic. This is actually a portion of a schematic. If I tried to fit the whole thing on here, it wouldn't quite fit. This is actually from a Universal Audio 1176 compressor. And as you can see here, there's a whole bunch of interesting symbols that we've got going on here. And each of these symbols represent individual electronic devices. Now we're going to take a closer look at all of this as we go, but I want you to understand when we start talking about these devices and what they do, we're also going to be looking at their schematic symbols. So we understand when we look at a document like this, when we see a symbol, we know what it's referring to and generally what that piece of equipment is supposed to do. You'll also notice that if you look closely on some of these, you'll also see that there is not just a symbol, but there's also notation about the part numbers, as well as maybe some identifying values. So please keep in mind when we talk about schematic values here, schematic symbols, this is the document that they fit into. Notice that all of these symbols also have connections on both sides, or sometimes some of them have 3 or more contact points. All right, so these symbols are not isolated things, they actually fit into a larger drawing. So please keep that in mind as we look at all of our individual electronic components. Our first major component we're going to look at is the transformer. The transformer is a foundational piece of technology, utilizes electromagnetism, which really is something that has proved to be a very transformational thing for all of us in all of our electronic devices. If we did not have electromagnetic transduction, the microphone that I'm speaking into right now wouldn't work, loudspeakers wouldn't work. This is stuff that really is very crucial to specifically our field, but a lot of technology in general. If you guys remember, we've talked about transformers before. Transformers are a big part of the AC electrical distribution system when we did our research on the war of currents. You'll remember that part of what made AC such an amazing innovation was that we could have our power generator much further away from the source. And we can also easily transform that voltage up and down, which is part of what made that happen. So this particular device is the technology that makes that work. Right? We step the voltage up very high coming out of the power plant. And then as we get closer to civilization, we step it down lower and lower. And remember, as we step the voltage up, that reduces our total current draw. Right? So we see the same amount of power conserved, but by transforming it to a higher voltage and lower current, that allows us to use smaller wires, lose less voltage over distance due to resistance. Right? So this is a pretty important thing for that particular system. It does some other things as well. But let's take a look at the basic technology that makes these work. Now, this illustration that I have here on the slide is a really useful academic illustration. Transformers don't typically actually look like this. There are some that you will find that do look like this, but usually they're constructed slightly differently. But this serves to show the purpose and show kind of how everything comes together in a very easy to understand format. Now, this wire right here, you notice this wire comes around this iron core in this case, and it wraps all the way around in a bunch of different coils. This side over here on the left is the primary side, right? So this is considered, in this case, the input side. And then over here we have the secondary side, which also has its own coil of wire. You'll notice in this particular example, there are different numbers of coils on both sides, and we'll get to that here in a second. So when current flows through this wire here, you will see a magnetic field that begins to build around it. Now, one thing that's very important to understand with transformers is that they require AC to function. If we did not have alternating current, we would not see a changing magnetic field. All right, so what's interesting about the discovery of electromagnetism, if you look back at the history of this, there is a professor that was experimenting with the very first battery known as a voltaic pile. It was invented by a scientist called Voltaire. Imagine that. We call a part of our electricity volts, right? So it's named after this guy. The voltaic pile was the earliest battery, and this was a pretty big innovation for a number of reasons. But part of the reason was because it allowed us to actually experiment with electricity. And so this professor had one of these voltaic piles on his desks, and he was lecturing to his students in class. And one day he happened to have a compass sitting on his desk, and he noticed that when he turned on the electrical supply, right, connected his battery, that the needle on the compass would move. And this was a curiosity to him. He didn't quite understand it at first. But through a series of experiments and events, he came to discover that whenever there's electricity flowing, there's also a magnetic field that is surrounding that wire. And so that's a pretty important principle. Magnetism comes along with electricity. They coexist. Wherever there's one, there's always the other. And so that's an important thing that makes this work. The interesting thing that he had discovered also, as we looked at some other experiments down the line, was that when they turned on a DC power supply, which is what that battery was, you would see a constant magnetic field. But when you used AC electricity, you'd have a changing magnetic field. So that's a pretty critical thing, because when we start to look at how that applies with a transformer, a constant magnetic field creates a single blip in the magnetic field, whereas changing an AC electrical signal will generate a constantly changing magnetic field. Okay, so when we have AC running through this wire here, we will see a magnetic field build up in a positive direction and then move to negative. And we will see that magnetic field run through this wire. And as it goes through this coil here, it gets amplified, right? Having the wires coiled like this amplifies the signal, the magnetic field. It strengthens it, right? It concentrates it in this place. And now it's wrapped around this iron core. That's what this illustration shows. Not every transformer has an iron core. There are also, iron is the most common, right? But you also see some steel core transformers. You might see some nickel core. There's some others that are out there. But iron is definitely the most common type. Now, iron is chosen here not because it conducts electricity. It is a metal, right? It will conduct electricity. But its job here is not to conduct electricity, because if it conducted electricity, we've got a wire here, we've got a wire connected to an iron core that conducts electricity, and then we've got a wire on the other side. So why is this different from a wire, right? That's not what's happening here, okay? What's happening here is that around this wire here, there is insulation, okay? And then, so there's no electricity actually touching that iron core, right? But when we run electromagnetism through this, right, the electricity generates that magnetic field, and that magnetic field is picked up by the iron core. So the job of this iron core is not to transfer electricity, but to transfer magnetic field. Okay. Now, when we get to the other side, we see the flip side of this relationship between electricity and magnetism working together. So on the secondary coil over here, this magnetic field then gets picked up in this coil here, and it starts generating an output current. Okay, so wherever, again, there is an electric field, there's also a magnetic field, and wherever there's a magnetic field, there's also an electrical field, right? So we see that we are converting on this side over here, we are converting an electrical field into a magnetic field. And then on the other side, the resultant magnetic field is then being converted to electricity. Okay, so that's kind of the basic premise behind the way a transformer works. Again, remember, the coil of wire is completely insulated. The core is insulated. The secondary coil over here is also insulated. So there's no electricity flowing. It is purely magnetism that is creating this process. Now, this seems like an awful lot of trouble to go through just to get a signal from one end to the other, right? But there are some really unique properties of transformers that make this whole process worthwhile. So you'll notice in this particular illustration that we have more than just a simple one-to-one transformer. We have, on this side, we have 1, 2, 3, 4, 5 coils. And on this side, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 coils, right? So we have twice the number of coils over here. What that means is when we run voltage through our primary coil, which has the 5 coils, and it's going to create a magnetic field of a certain strength because of the concentration of the magnetic field. Remember, that concentration happens with the coils of wire. On the second side, because we have more coils of wire over here, that magnetic field gets picked up in a stronger concentration. And so we actually get more voltage out. Now remember, keep in mind, voltage is just one of our electrical properties, right? We also have current, we have resistance. Remember, voltage and current together gives us wattage, right? So we're going to see the same wattage on both sides. But as the voltage goes up, remember the current goes down, right? That's just the way it works. Voltage times current equals wattage. So in this case, if we run in 110, 120 volts over here, because we have twice as many coils, notice we get twice the voltage out. This is what's known as a step-up transformer. A step-up transformer brings in voltage on one side, and then it spits out voltage that is higher on the other side. This also happens to be what we would call a 1 to 2 transformer. So the 1 to 2 transformer is going to tell us what's called the turns ratio. The turns ratio tells us how many turns of wire we have on one side versus the other. So that turns ratio is going to tell us not only how many turns, but also whether we're stepping up or down, and by how much. So in this particular case, this would be a 1 to 2 transformer. It tells us that if we run 1 in to the primary side, we get 2 out. When we look at the secondary coil, or excuse me, the second transformer down here below, you'll see that it's in reverse. What's actually happening in this picture is basically the transformer up top has been flipped around. And what's really interesting about all this is that you'll find that transformers really don't care which side you use. Some of them are designed for very specific reasons, and it doesn't really work too well to flip them around. But in this case, all we've done is take the exact same box, flip it around, and now we're calling one side a different name. The transformer doesn't really care. It's a very simple device. It just allows the concentration of magnetic fields to be carried from one side to the other. So in this case, though, because we have 10 turns on the primary side and we have 5 turns on the secondary side, this would be a step-down transformer. So where the one up top was a 1 to 2, the one down here is a 2 to 1, right? If we run in this voltage here, we're going to get half of that on the secondary side, right? So this particular transformer actually is sold in stores. It's called a buck boost transformer. Bucking the voltage or boosting the voltage. This is something you can go buy at Granger or similar places that do some kind of, or maybe Tractor Supply Company, right, where they have some kind of low-level industrial stuff that you can buy. This is really helpful if you're trying to run a piece of American equipment over in Europe, because remember, European voltages range between 220 and 240, and American voltage is 120. Right. Notice this diagram also lists 110 as an option. That's just to indicate that sometimes we actually have as low as 110 because of voltage drop from the service entrance on the building. So if you had a buck boost transformer like this, you could, let's say maybe you're setting up a piece of equipment that you normally use here in the States that does not have an auto sensing power supply, and you need to run it on a tour in Europe. Then you can simply plug this in. It will take this 220 or 240 volts, and it will step it down to something that your American piece of equipment can run off of. Or vice versa. Let's say we've got somebody coming from Europe and coming to the United States. We could simply reverse this transformer, and our low voltage here will be stepped up to the high voltage that their piece of equipment needs. Right? So this is a very simple example, but it is a very common one. There are other things that transformers do as well. Let's go ahead and take a look here um, at a little bit more of a description here. So the process that we were just talking about is known as mutual induction, right? So we've got electromagnetic induction happening in both directions on both sides, right? So electrical to magnetic, magnetic to electrical. Again, remember, keep in mind we need varying current, right? So we need alternating current. We need current that flows in different directions because it's the change in the magnetic field that generates the, change in the current that generates the change in the magnetic field, which then, of course, generates the change in current on the other side. If we run DC through a transformer, it will effectively block it, which is why, by the way, the Shure SM58 that I'm talking into right now is not damaged when I turn on phantom power. Remember, phantom power is a DC power source, and my Shure SM58 here has a small transformer on the back end, which is serving a different purpose than stepping up or down voltage. We'll talk about that here in a second. But it effectively blocks the DC and keeps it from damaging the microphone element, among other things. So this is describing our turns ratio that we've discussed, right? If the primary and secondary sides have differing amounts of wire, which most often they do, the input voltage is changed. So fewer turns on the secondary means a step down, right? If we have more turns on the primary, fewer on the secondary, which is what we saw on the bottom here, right? This particular example here has more turns here, fewer turns here. This is a step down transformer. And if we do vice versa, right, that would be a step up transformer, right? Now keep in mind, we've been talking about voltage a lot, but this also does affect the impedance of things that we are interacting with. So if you guys remember, I believe we've discussed this a little bit. So we've learned about resistance, right? Resistance is the opposition of the flow of electrons, but impedance is effectively the same thing. However, it is resistance for AC, right? So when we introduce AC, alternating current, we introduce frequencies, right? At the very least, if we're dealing with power, we're dealing with a frequency of 60 hertz. And that frequency has an impact on the level of resistance. Oftentimes you'll see that when the frequency goes up, so does the resistance. And so impedance is a rather complex relationship. And so we see this, though, transformers, by having specific turns ratios. A higher number of turns means a higher impedance, and a lower number of turns means a lower impedance. So you'll see here some examples. So if we have a high impedance instrument, right, let's say the output of a bass guitar with a pickup, and we want to interface that with a low impedance microphone preamplifier, having a transformer between the two will help accomplish that quite a bit. If you guys remember the discussion that we had in sound reinforcement last semester, you'll remember that this is effectively what's happening inside a direct box, right? Remember, direct boxes take our instrument signals and convert them to something that works with a microphone preamp. There are other ways to do this, by the way, but the simplest direct box is simply going to have a step-down transformer inside that matches the high impedance on the primary to the low impedance on the secondary. Next, if there's anybody who has a tube guitar amp or has worked with them before, if you look on the back of your tube guitar amp, you're going to see a number of tubes, and you're probably going to have anywhere from 2 to 6 very large tubes. These are your power amp tubes, and the output impedance on the power amp tubes is very, very high, but these are directly supposed to drive the loudspeakers, right? These are what actually push the energy to the loudspeakers and generate sound out of your amplifier. But loudspeakers are very low impedance, If you guys remember our discussion on parallel and series wiring, we talked a lot about it. We talked about these examples quite a bit. And loudspeakers typically have impedances of 2, 4, 8, 16, maybe as high as 32 ohms, whereas your power amp tubes are looking at something like 10,000 ohms coming out. So that's quite a bit of a mismatch. And by introducing an output transformer between the power amp tubes and the loudspeakers, we can match those two together and create an effective relationship between the two where they can actually do their job. So those are a couple of examples there for impedance matching. Now I don't have this on the slide, but there is one more very important application for transformers, and that is the job of isolation. If we have a 1-to-1 transformer, that means a turns ratio of 1-to-1, the turns are the same on both sides, primary and secondary. That allows us to run signal through a transformer without changing it fundamentally, but it does allow isolation. We have the source signal, we have the transformer, and we have the destination. And the transformer effectively serves as a go-between between the two. It's almost like a translator. It allows the input and the output to have a relationship, to actually pass signal between the two, but they never actually interact with each other. So this is a very important function of transformers. You see this a lot. We've used this in several of our projects. If you guys have been in sound reinforcement, you know that we deal with these with a microphone splitter. Right, so if we're trying to split our microphone signals to our different systems for front of house and monitors, or maybe more, then having transformer isolated splitters is the only way to really do that. If you've been in live recording techniques, also we've talked quite a bit about this as well. So those are our three applications. Transformers are primarily used for voltage step up and down, impedance matching, and isolation. Now let's talk about schematic symbols. So these are some examples of schematic symbols. One thing that's important to remember as we look at these individual symbols, remember that they are designed to fit in a larger puzzle like this. So this symbol is isolated on this slide here, but if it were actually in use in a circuit, you would see these connection points here actually connecting somewhere in a circuit. So we'd see a line coming out here, a line coming out here, maybe a line coming out here. It just depends on exactly how it would be laid out in the circuit. So these are our 4 connection points. We have the high side here of the primary and the low side of the secondary here. And here's the high and low side of our primary. Excuse me, this is the primary side, this is the secondary side. So we would see all 4 of these connected. So notice there are these loops of wire here, right? We see these on both sides. So these represent the turns, right? The coils of wire. Generally speaking, you're going to find that the schematic symbol tends to approximate the actual turns ratio. So in this case, we see there's 2 coils here and 4 coils here. So my guess would be that this is actually a 1-to-2 transformer or something close to that. Even if it isn't exactly 1-to-2, it might be a 1-to-1.75 or something like that. They tend to approximate the turns ratio. Also notice that there is a couple of lines here. You'll see some variation on this, but there's always going to be something in the middle here to show that there's a core of some sort, right? This is what's carrying the magnetic field between the 2 sides. Okay, so that is our step up transformer, right? We have fewer coils here, more coils here, so this would be a voltage step up or an impedance step up. Over here we see that symbol is reversed, right? So we've got a step down transformer in this case. Now, again, this is a relatively simplistic transformer. You do find these. Again, we talked about the buck and boost transformer. If we find an isolation transformer, we'd see this symbol or something very close to it that has the same number of coils on either side. Most of the time, though, we're looking at stuff that's a little bit more complex. So let's take a look at this next example. This next example here shows us a single primary coil with multiple secondary coils coming out. This is something that you might see in a typical power supply. So in a power supply, transformers do the job of stepping voltage up and down, but they don't have single voltages, right? Like we talked about with the AC distribution system, we've got a single voltage coming in, and it needs to be transformed to a single voltage on the way out. But this, if we were trying to drive a piece of equipment, let's say it's a tube piece of equipment, right? Vacuum tubes typically require several different voltages to work. They require a low voltage, high current supply for the filament. The filament is what heats the tube up and actually makes everything work. So we're looking there at about 6 volts or so. And when we also have to supply a high voltage signal to it. Depending on whether we're dealing with preamp or power tubes, we're looking at maybe 230 volts all the way up to about 350 volts. And that's what actually allows the electrons to jump from one side to the other and actually make the vacuum tube function. So those two voltages need to be generated from a power supply in a tube device. And in this case, we actually have 3 different secondaries, so maybe this piece of equipment also needs an additional voltage. Maybe we're driving some relays, or we've got some other circuits that require a different voltage. So the job of the transformer in a power supply is to generate all the different voltages that that piece of equipment needs. While the transformer is the first device that we're talking about in this part of the semester, a transformer is actually typically the last device to be designed as part of a unit. So when we design a particular product or a piece of equipment, we have to look at what we want it to do. Then we have to actually design it to do that job. And then once we do the design, we have to figure out exactly what the power requirements are. And then we design the power supply around that, and then the transformer is designed specifically to drive that power supply. So this really is something that is custom made in many cases when we're talking about power supply transformers. The way that this is constructed, let's take a look at this next slide here. You're going to notice the construction on this is very different from what we've just seen in our examples. Another example here is much the same. So what we see here, instead of a core that's in the shape of a square with wires wrapped around it, we do see a square core, but the coils of wire are actually inside the core, right, rather than wrapped around it. And this is actually the most common construction for this type of transformer. So what you see is the coils of wire are inside, and they are actually layered on top of each other. So all the primary and secondary coils are actually sandwiched together in kind of this concentric donut inside. They're, of course, isolated from each other. They have insulation on their own wires. They also typically have paper or plastic, or sometimes some rubber wrapped between the layers to keep them from interacting with each other electrically. But because they're stacked on each other and they're inside that core, they're always interacting magnetically. Right, so we see the same basic functionality that we saw in our academic kind of diagram here, but in actuality, this is a more typical construction. So you can see in both of these cases, we don't have simply 2 terminals on both sides, right? We've got some additional terminals that are present here. To really know what these terminals do, you have to really look at some documentation. You can certainly run some voltages through this stuff and figure out what's coming out on the other end, but without really knowing how those coils are configured and wired together, things can get really confusing really fast. So if you are opening up a piece of equipment that has a bad transformer and you're trying to find a replacement for it, you should be able to find, again, a schematic that has some of that information. Or you can look at the owner's manual. You can call somebody who's done some service on these before and knows a little bit more about it. But just blindly grabbing a transformer off the shelf and hoping that it's going to do the job for you usually doesn't work very well. So transformers, again, very, very important. As we continue on through the semester, we are going to talk more about how a power supply comes together. But remember, this is that kind of first foundational piece. When electricity comes in from the wall, it's going to hit one of these first, right? Because we have to generate those multiple voltages out that we need for our piece of equipment to function. Now, there is another type of transformer, and that is the auto transformer. the autotransformer, or sometimes called a toroid. The reason it's called a toroid is because that's actually the proper geometric name for this type of donut that you see over here on the right. Um, this is a kind of a donut core. You'll notice that it doesn't really have anything in the center, right? It's just, we've got this, let's just say it's an iron core in this case, right, in this toroid shape. And then we have, notice, only one coil of wire. This is very different from the traditional, what we call the EI laminated transformer, what we saw in the previous slides. That's the letters E and I laminated, so an EI lam transformer. That has to do with the shape of the layers of the core as they come together. It's very different from an EI lam transformer because with one of those we had multiple coils of wire that were within the same magnetic field. Here we have one coil of wire. Now we are still dealing with electromagnetism, right? But this device actually functions a little bit differently. So there are different taps or different wire connection points placed at different places in the coil. And each of these taps represents a certain percentage of the input voltage. Let's go ahead and take a look at this diagram here, and this explains it a little bit better. Now you'll notice in the center here we've got this coil, right? It has been straightened out, but this represents the coil that goes around the toroid, okay? On the primary side over here, you'll notice we have a connection point here and a connection point here. Now, by the way, this is, I guess, a schematic symbol here for an autotransformer. I've never actually seen one represented quite like this, but this really explains very well how it's laid out. So if we were using this as a transformer in a power supply, which it very commonly is, we would see down here, this would be our neutral connection, and up here, this would be our live. So this is the actual voltage coming in. You'll notice that this is connected about 80% of the way up on the transformer. So there's a little bit of coil that goes beyond this, and we'll talk about that in a second. Over here on the secondary side, you're going to see that there are a bunch of different places where we could grab our voltage. So on the back end of this, we would have our neutral connected here, we would have our live connected here, but we have all these different options. So let's just say that we connect it at this point up here. So we can see that the neutral is connected to both sides of this coil here, the live is connected here. So what we would see is that the input voltage and the output voltage would be the same. Right? This would do nothing other than just provide some isolation. However, if we were to connect up here, what that would mean is that this coil has now lived in that magnetic field just a little bit longer, and now we would have a higher voltage. So if we were to connect down here, this means that that coil has lived in the magnetic field a little bit less. So that means that this would actually represent a lower voltage. And then this one, because it's lived in the magnetic field, would represent an even lower voltage, right? So this shows us that this is basically grabbing a percentage of the voltage, right? So if we were to grab, let's say this one right here, this is about halfway up this coil. So that means we'd get about half the voltage out on the secondary side. So these can be designed to be pretty significant step-up transformers as well. It's easy to see how they can be step-down transformers, right? You can just grab less than 100%. What if this primary side, though, was actually connected somewhere in the middle? Let's say the primary side was connected here. That means that when I grab something from up here, this is now double the voltage, right? So it just depends on how it's all configured. Right? We are essentially using this one coil as both the primary and secondary. Now, the reason this works, by the way, remember that we're not grabbing something that is just purely electrical, right? It is the same coil, but we've got the magnetic field involved here. So the magnetic field is a really interesting thing. Remember that electricity and magnetism actually coexist, right? Anytime there is a flow of electrical current, there's a magnetic field around it. Anytime there's a magnetic field, there is some electrical potential involved. So what happens is, remember, we're using this for AC, and AC alternates between positive and negative. Now, as it alternates between positive and negative, so does the magnetic field. However, they don't really go at the same time. They actually kind of like one lags behind the other a little bit. So when you have, if you run electricity in, that magnetic field kind of follows it, and then when the AC alternates and goes down to the negative portion, now all of a sudden there's a positive magnetic field that says, "Wait a minute, I got to play catch up." And so what happens is this negative portion of the AC wave is actually being fought by the positive portion of the magnetic wave. And so there's this back and forth tug between the two. We're going to see this a little bit more with the next device that we look at. But this is what's actually happening inside this coil. So again, it's not just a simple wire. We've got this interaction of the magnetic field. We're concentrating that magnetic field and increasing this particular effect that we're talking about up here. Okay, so autotransformers or toroids. Now, why would we pick one of these over the other? Well, so autotransformers tend to be a little bit cheaper to manufacture. They also tend to take up a little bit less space, and they also tend to throw off less electromagnetic radiation, right? They tend to concentrate it a little bit more. This can be a really big advantage for us because if you think about this, if we have this in the power supply of a piece of audio equipment and we have audio wiring running through or next to the magnetic field here, that wire, if it's within the magnetic field, is going to pick up that electromagnetic signal, right? That magnetism is going to generate an audio signal on the wire. So if we have a smaller magnetic field, that keeps our power supply from interfering with our audio signal. If we have a big enough power supply, oftentimes they are separated from the device to make this an even lower probability. But if we have to have the transformer in the power supply in the device, toroids are often preferred for a variety of reasons. But you will see both. I see a lot of these EI lamb transformers in guitar amps, and you see a lot of this more in like rack-mounted gear. So let's refresh ourselves real quick on the schematic diagram here for an auto transformer. Again, they don't often quite look like this, and they wouldn't be labeled as the primary and secondary. But again, typically the transformer is going to be laid out that way. Right on the left-hand side, we would call that the primary. On the right-hand side, we'd call it the secondary. There is one other variation of the auto transformer, and that is the variable auto transformer. So this is made by exposing part of the winding coils and making the secondary connection through a sliding brush. So let's jump back here and let's take a look at this. So let's pretend that our exact configuration here is exactly the same, but let's pretend that all of these connection points just don't exist. What we have instead is this is our connection point, and there is a brush that is actually physically touching the coils here. So what that means is we can move that brush up or down, and as we do, we are continuously varying exactly where we tap off of that transformer. So that means by turning a knob, we can adjust voltage up and down nice and smoothly for whatever reason we might need. Here's a picture that shows that. So again, this is a variable auto transformer. We've got our big core, and you can see the copper windings very tightly spaced. You can see that they've been kind of ground down on the top here. You can see this nice smooth surface right here. And then this little guy right here, this is the brush. So this brush is making electrical contact, just like a wire would, with these particular parts of the winding, right? And so as it does that, as we move it along this line here, right, around the arc, okay, then we would be grabbing different voltages out of this device. Now, you guys have used one of these before. You just probably didn't know it. One of the most common uses for these is for dimming lights. So in Studio B, you will notice, if you go in there, that we don't have traditional light switches. We also don't have the push-button dimmers like we have in Studio A. We'll get to that here in a second. But we actually have one of these guys in the wall controlling our lights. Now, why would we do that? Well, number one, it's very common for studios to have the ability to dim lights and set moods. We don't do a lot of mood setting when we're doing classes, but we definitely built the studio to professional standards. So we want to be able to dim lights, right? That's just kind of a given in studios. But why can't we go to Home Depot or Lowe's or Ace Hardware and buy the same dimmers that you might have in your house? Well, those dimmers work a little bit differently. So with a variable auto transformer, and by the way, often called a variac, we'll see that term here on the next slide. With a variac, we're simply adjusting the voltage up and down. And as we do that, it will dim our lights, right? If we send less voltage to a traditional incandescent bulb, it simply dims. The things that you find at Lowe's or Home Depot, these actually work a little bit differently. Rather than reducing the voltage, they actually turn the voltage off for a short duration, depending on how bright you want it to be, right? So if you want it at full brightness, it just never turns the voltage off. If you want it at half brightness, it's going to turn the voltage off for half of the given cycle that it's running through, right? The rate that it's switching on and off. It's going to turn off the voltage for half the time, and then it's going to turn the voltage back on for another half of the time. Now that's effective, but the problem is that it throws a whole bunch of harmonic garbage back on the electrical line. And that's the last thing that we really want in a context where we want our audio to be nice and clean. If we were to do that, that would give us some pretty nasty hums and buzzes in our audio. It's actually, I've got a funny story related to this. I used to be an intern at Dark Horse Recording out in Franklin, Tennessee. It's a really cool studio. It's basically like a tree fort destination studio. So the whole thing is like a big log cabin, and they've got a couple of really cool rooms. They've got the A room, which was the lodge. They've got the B room, which was the cabin. And they were both cool for their own things, but they were all kind of built by a gentleman named Robin Crow who had a real passion for this, but he didn't have a lot of the technical know-how. And so in several places you would find a few quirks, a few corners that might have been cut unintentionally, just because that you just didn't know any better. So, for instance, in the main building, in the upstairs area, you had the lounge area, you had the lodge, the big studio. We also had a small, tiny little overdub suite that often didn't have a lot of equipment in it. It was kind of, we'd move stuff in and out. And you had the offices. Down below, there were actually hotel rooms. So people could come and book the hotel rooms and actually camp out and stay there and do their projects. So downstairs with these hotel rooms, they weren't always in use. And so the owner was very cost conscious, really wanted to save some dollars when he could. And so he would always, in the evenings, go downstairs and say, well, hey, if there's nobody here, we're going to dim the lights. Now, he installed traditional dimmers, right? The kind of thing that you would go buy at Lowe's or Home Depot that throws harmonic garbage onto the lines. And so we would often have this experience up in the lodge where we would set up the session, we'd be running all day, everything was great. We'd take a dinner break, and then when we come back after dinner to knock out another track or two before calling it a night, all of a sudden we'd have this nasty hum on a couple of our audio lines, right? And it didn't take us long to figure out, oh, that's just because Robin went downstairs and dimmed the lights. So if we went downstairs, we either turned the lights all the way off or turned them all the way on, the hum went away, right? Because if the dimmer is actually, if it's all the way on, right, it's never switching it off, it doesn't do any harmonic damage. If it's all the way off, of course, there's no switching on and off at all. It's just off entirely. The funny thing is he thought he was saving money, but actually what he was doing, he was actually using a little bit more electricity, because guess what? The dimmers actually used electricity to function. So there were a couple of issues that were really wrong with that approach. But this is why we would use a variac to control our lights. There's also another reason that we would use a variac. We can also adjust the voltage for a variety of other reasons. This actually is a piece of test equipment. So we would normally have one of these on our bench when we're testing things. So remember, when we talked about our test equipment, we looked at The multimeter, we looked at our signal generators, we looked at our oscilloscope. Right, those are kind of the three basic ones. This is really the fourth. The reason we're talking about it here is because I want you to understand exactly how it works. Right, it is a transformer. Right, but this really should be considered a fourth vital piece of test equipment. Um, so voltage adjustment. Well, let's talk about why we would want that on our test bench. If we have a vintage piece of equipment that's not been powered up in a very long time, one of the worst things you can do, in fact, probably the worst thing you can do, is simply plug it into your bench and just flip it on. There are some components inside that simply do not like to sit dormant for a long period of time, specifically the capacitors. Now, we haven't talked about those yet, but capacitors are essentially small short-term batteries that store a charge for a brief period of time, sometimes very, very short periods of time, talking in the microsecond range. But they are very critical to the way the device functions. And if they've been sitting dormant for a while and you simply hit them with the full voltage that they're normally operating at, you run the risk of damaging them or destroying them. Usually that's not something very catastrophic, but it might be catastrophic to your wallet if you just spent $20,000, bought yourself a used Fairchild compressor from back in the 70s, and they no longer make some of those parts. You just simply plug it into your rack and flip the power switch. The light comes on for a half second and then it goes dark. You all of a sudden are doubting your investment, and for good reason. All right, so if there is a piece of equipment that's in a similar state like that, where it's been sitting on a shelf for a long time, maybe a guitar amp as well, right? It's very common to, instead of just turning it on, put it on a variac. And as you adjust the brush up, you can bring the voltage up, the line voltage that's powering the device. And so you can go from 0 volts to 20 volts to 30 volts to 40 volts, all the way until you get to the full 120. So this gently brings the device back on and allows those capacitors to slowly wake up. How quickly do you do this? Well, it just really depends on how fanatic you want to be, on how careful you want to be, on how critical this particular piece of equipment is, on how long it's been sitting. You'll find some people that are comfortable bringing something up over the course of 15, 20 seconds. You'll find some others that might take a day, a week, a month, right? They just kind of let it sit for a while and slowly just bump it up a little bit and then just go on about their day and come back the next day and bump it up a little bit more. Right, so people can get a little bit fanatic about this, and I don't think there's really cause to do anything over that particular duration of time, but I can certainly understand the level of caution considering some of the investment that goes into vintage pieces like this. Lastly, in this same voltage adjustment category, again, if there's anybody who plays tube guitar amps, or let's face it, you're all going to work with people who play tube guitar amps. If you have an older tube guitar amp, you can actually modify the tone a little bit by adjusting the voltage. So some of these guitar amps really love to work at exactly 115 volts or 120 or 110, right? You'll see this kind of rated on the back, what's coming in on the cord. It'll say it's designed to run on this voltage. If you drop the voltage a little bit below what it's supposed to be, you actually get an interesting tone out of the amplifier. It has a little bit more um, sloppiness to the tone, right? It's called tube sag, so it just sounds like a softer tone, right? It has a little bit less aggressive, less clarity, right? The amplifier's just not running. It's almost kind of like the amplifier's drunk a little bit, right? It's not running at its full capacity. It's a little bit diminished. And that could be an interesting and desirable tone, and that you will find that some session guitar players actually travel with a variac to be able to get that tone. Others travel with a variac just because they want to make sure that they're running the exact voltage in that their amplifier needs to function properly. So that's something that you could use yours at the shop for, right? If you had it on the bench, you could offer that as a tool for your guitar players that come in to work. Okay, so that finishes our discussion on transformers. Just remember, we've got our traditional EI laminated transformer, right? We've got the core around the outside, and then we've got the individual coils wrapped inside, insulated from each other. We usually have multiple taps on these. If we only have the two taps, we could be dealing with a simple step up or step down transformer. We could also be looking at an isolation transformer if the turns ratio is a 1-to-1 ratio. And then we have the auto transformer. It's a single coil of wire around a single core. And then we have our different taps that allow us to grab different voltages depending on where they are on that coil. And then finally we had the variac, or the variable auto transformer, which takes that idea and adds a movable brush, which allows us to adjust our voltage up or down. Great test piece of equipment for voltage adjustment, also is a common tool for doing lighting dimming. Next we move on to inductors. Now inductors are actually very similar to what we just looked at. So if you'll notice just from these particular pictures, we're going to see a core that's here, and then we're going to see a coil of wire wrapped around that core. It seems like we're riffing on a theme here, right? You'll notice over here we've got a slightly different construction, but we've got a core and a coil. Here we've got a core and a coil. Here in this particular one, we don't actually have a core. We have what's called an air core inductor. The general principle here is the same. So what are we dealing with? Well, an inductor is actually a very small version of what we just looked at with our auto transformer. Right, so with our auto transformer, we have one large core and one large coil wrapped around it. With an inductor, we actually see exactly the same construction on a smaller scale. So this uses the same principles, right? This is still electromagnetic induction. By the way, I want to point out real quick, remember I told you that these coils of wire are actually electrically insulated. This stuff up here looks the color of copper, but this is actually not exposed copper. You'll notice down here that this lead here has been tinned. It's got the solder pre-applied, and then you see this little line right here actually has, we've stripped back some of this insulation. So it's very thin copper-looking insulation that goes around all of these over here, right? Same thing with transformers. So this keeps the electricity from touching where we don't want it to. So, but these areas here, this is where we'd actually solder it into the circuit, right? Same thing over here. Okay. So inductors are small-scale auto transformers, or another way to state that, which is a little bit more accurate, is that auto transformers are simply large-scale inductors. Now, what does an inductor do? Well, we could certainly use it like the transformer, as we saw with the auto transformer, but typically on a small scale, we're talking about something a little bit different. Okay, so we're talking about this idea of the magnetic field opposing it, the electrical field, and vice versa. So this particular principle is called Lenz's law. We talked about this with the auto transformer, right? Remember, if we've got our alternating current wave, right, the magnetic field kind of lags behind it. So when we increase our voltage here, the magnetic field rises to follow it, and then as soon as we reverse to the negative here, we still have a positive magnetic field that is kind of lagging behind, and that positive here fights this stuff down here. And so we have this kind of push and pull relationship between the electricity and the magnetism. Right, so this principle is called Lenz's law. Lenz is somebody who actually did a lot of research with electromagnetism. And because of that, by the way, when we talk about inductors, we use the letter L quite a bit in reference to that. This diagram over here on the right helps to illustrate a little bit of this. The reason that maybe this makes it make a little bit more sense, right? So here we have an electrical cable, right, and we have current flowing in a specific direction. You'll notice that there's a hand wrapped around this. So this is known as the right-hand rule. You'll read about this in your textbook as well. So the right-hand rule states that, this is just an easy way to remember this, right? If you wrap your hand around an individual conductor that's carrying electricity, if you point your thumb in the direction of the current flow, your fingers that are wrapped around show you the direction of the magnetic field. So you can see here the magnetic field here is rotating counterclockwise when the current is flowing up in this direction. Okay. Now remember, with alternating current, right? Alternating current means that not only does the voltage go up and down, but the current actually flows backwards and forwards. So we have current flowing in a specific direction, but it doesn't stay flowing in that direction. It actually reverses, right? So as that current flow reverses, we have this magnetic field already rotating in this direction, right? But the current's wanting to flow in the opposite direction. So this magnetic field is going to fight it until ultimately this current that's reversing is going to overcome this magnetic field, reverse the magnetic field, and then guess what? It happens again. We reverse back and forth, back and forth, back and forth, back and forth 60 times a second when we're dealing with alternating current electricity, right? So what happens is ultimately inductors are resistive to changes in current. Okay, so the best analogy here is a water wheel. Remember that we used water as a great analogy for electricity in general. And I'm sure you guys have seen mills before that use big water wheels to help drive them. Even if you've never seen one in person, I'm sure you've seen a picture, right? So when we look at the way that works, if the mill is at rest, nothing's moving, right? And then we start the water flowing on the wheel. The wheel doesn't immediately start turning at full speed, right? It takes a little bit of time to ramp up to full speed. Then if we were to shut the water off, the water stops flowing, but the wheel doesn't stop moving, right? The wheel keeps turning because it has momentum, right? So what we have here with our Lenz's law example here is that we have magnetic momentum, and that is something that takes a little bit of time to get moving in one direction or another as the current either starts or stops, flows in one direction or the other. Okay, so these are effectively, inductors are effectively resistors when it comes to alternating current. Now, I won't get into the math behind this, but if you were to look at the math behind how all this works, finding the inductance and the reactance and all that stuff dealing with AC that gets way more complex, you'll find that frequency is a big part of that formula. Take a second and think about it. What is the frequency of DC electricity? Does it alternate like this? The answer is no. Right? So if we have a frequency of 0, right, that means that inductors, they don't have any impact on DC electricity, but they do on AC because of the frequency, right? Because we have the magnetic field changing directions with the electrical field, and they're not quite in sync with each other. They're fighting each other. Now, here's another illustration of that, and this is going to be a pretty big deal in a lot of circumstances, but I'll give you a couple of examples here where this is really useful. So remember that with alternating current, we actually have two things that are alternating, right? We have the voltage that goes higher and lower, and we have the current that also goes positive and negative. Most of the time, these are in sync, so they are actually working in tandem together, right? And there's nothing that can separate them until all of a sudden we meet some inductance, right? So inductance, right, that's going to slow down the flow of current, right? And what it's going to do, the voltage rises and falls just like it normally does, but the current is slower. And so what we see here is we actually see a shift in the current. Now, if these two waveforms here, if we were simply going back to your first semester and talking about phase, if we were to combine these two waves, what would happen? Well, we'd see some measure of cancellation, right? Because in this case, they're offset by 90 degrees. Remember, we talk about our waveforms from 0 to 360 degrees. And so because we have offset this by 90 degrees, there are some areas where we have a negative and a positive. These are going to cancel somewhat. Here we have a neutral and we have a positive, so that's going to be a positive, and so on and so forth, right? So there's going to be a complex interaction between the two. There's going to be some loss because of phase cancellation. Um, so this, by the way, is one of the principles that is used to equalize things, right? Equalizers, the traditional passive equalizer actually uses inductors heavily to create a phase shift between the voltage and current waveforms and actually cancel specific frequencies. Um, it's a very complex topic, but at least this gives you the underlying principle. The other thing that's important to understand is as we talk about inductors, we're also going to talk about capacitors. Capacitors kind of do the opposite of inductors. And so we're going to see that we can actually create some serious issues right here, right? Remember that we have voltage and we have current, right? And when we multiply these two together, we get what? We get wattage. If we're multiplying these things and they're in sync with each other, we get nice, useful power. But if we have a shift in phase between the two, we can actually get, at some points, we can get negative wattage, which is kind of a weird concept, negative power. And we can get into situations where we're actually wasting power. It's a little bit beyond the scope of what we talk about in this class, but it's an important concept to understand that your voltage and current are actually two separate waves, and they have to be maintained in sync in order for power to be an effective thing. Now, so we looked at these inductors here. So these are classic examples of inductors. You will also see some that are itty bitty tiny inductors. These don't actually look like inductors. In fact, if you guys have messed with any electronic stuff in the past, you know, these actually look a lot like resistors. They've got, you know, the small kind of peanut-shaped body. They've got the color code on there and the two leads on either end. What really sets these apart in this case is the color, really. I've never seen like a seafoam green resistor in any context whatsoever. I'll be honest with you, I actually haven't used any inductors quite this small. Most of the inductors that I have seen or had interactions with are significantly bigger, at least the size of like a silver dollar. So you do find these, they're not quite as common. As far as the color code on here, I'm unsure of whether it's exactly the same as the resistor color code, but that's what Google University is for. Right? Now, schematic symbols. If we look at our schematic symbols here, you're going to notice a few similar themes. So for our fixed values here, we've got the two cores. Excuse me, we don't have any cores. We have the two coils. Notice the art is slightly different, right? You'll see some variation just depending on who drew the schematic, and sometimes you'll see variation on where the schematic was generated, whether it was something made in the United States, whether it was something that that was made in Europe. But on the left we have the fixed value inductors, and again remember our connection points are here and here and here and here on these symbols, right? So these would be going on to different parts of the circuit. Okay. Over here on the right we have iron core inductors. Notice there's variation on this as well. We've got the coils. Sometimes the core is inside, sometimes it's next to it. So slight variations, but the same idea is there. Next we have the variable inductor. So this is a theme here as well that we're going to see a lot. Anytime we have a variable component where we can simply adjust a knob or a dial and change the value, you'll see the traditional schematic symbol here with an arrow at a diagonal passing through it. So that would take any fixed component and make it variable. Now keep in mind with this symbol, with a variable component, we still only have two electrical contact points that interface with the schematic. That's a little bit different from the variac, right? So by the way, notice, hey, a variac is a large inductor, right? If we look here, we can see we actually have three electrical contact points. So this is the beginning of the coil up here, this is the end of the coil here, and then here is the output of the brush. So this is different, right? It is a variable inductor, but it's a little bit different in that it has the actual tap coming out of the center there. With the other variable inductor over here, this simply has the two contact points, and then by changing a knob, it just changes the value that comes out. Over here, the tapped inductor, which is, by the way, this would be a fixed auto transformer, right? We've got our single coil of wire here, so that's two contact points here, right? And then we've also got this contact point here and this contact point here. So this would be the low side, this would be the high side, and then these would be two taps coming out from the middle there. Okay, so several different variations on the same theme. If you understand the basic premise of how all of this comes together, that should make fairly good sense. Next, we move on to the diode. The diode is a pretty critical component. The diode was actually the very first vacuum tube that was invented, by the way. You'll notice the device that we're talking about today does not actually have a vacuum tube in any of the illustrations, and that's because we're talking about the more modern version. However, when you guys do your paper on vacuum tube technology, you're going to be reading about the Fleming diode. This was the very first vacuum tube that allowed current to flow in one direction and not the other. And this was the beginning of being able to convert from AC to DC and starting to see some amplification come into the world of electronics, with one additional advancement after that. So the diode was a pretty critical component as well in the history of electronics world. So as you may have surmised from my little summation there, right, a diode is an electrical device that allows current to flow in only one direction. So it is effectively kind of like a water valve, right? Only we're dealing with electricity. And again, those of you who have done anything with tube devices, whether it's amplifiers or whether it's stuff in the studio, you may know that the Brits call vacuum tubes valves. And this is why, right? Because the original vacuum tube was like a valve. It allowed electricity to flow in one direction, but not in the other, right? It would shut when it tried to flow in reverse direction. It has two active terminals, the anode and the cathode. We're going to see a diagram here that shows those two. The most common function of a diode is to limit flow of current to a single direction, the forward direction, while blocking reverse flow. So here's an example, not only of what a diode looks like and how it's laid out, but also talking about testing one as well. So you can see here we've got a simple 1N4001 diode. This thing probably costs about 3 cents, and it is a very common model number. This is like the basic diode that you'd see out there on the market. You can see that on the left here, well, I guess it depends on your perspective, right? But this on the right here, this is the anode, and this over here on the left is the cathode. You can see also here the schematic symbol. So notice there's an arrow with a line, right? So it kind of shows you the function of the device in the symbol, right? The current can flow this way, but if it tries to go back this way, it gets blocked by that line, right? So you can see the way that we're actually testing this with the meter over here. Notice, by the way, what mode we're in, right? We're in resistance mode, right? We're trying to see, is current getting from one end to the other? We are testing continuity, right? So if we have continuity, that means that current is flowing from one direction to the other. If we don't have continuity, that means it's being blocked. Right, so this is a great way to test a diode, is hook it up properly first, right? Notice the anode is the negative, cathode is the positive, right? And it should work this way. If it doesn't work, then we've got a bad diode. If it works this way, that's great. Remember, its job is to allow current in this direction. It should not allow current to go back, right? So how can we test that? We simply reverse our leads, right? Here we have the negative, here we have the positive, right? Why don't we simply swap them? If we swap them, that means we're trying to run current in the opposite direction, and it should block it. If it doesn't block it, then we've got a bad diode. So this is just basically leak testing, right? Making sure that electricity flows only in one direction on these devices. I will tell you though, generally speaking, if you suspect a diode like this, it's important to understand how to test them for sure. But if you suspect a diode like this being part of your problem, um, just replace it. Again, they cost like 3 cents. And this is the kind of thing, it doesn't hurt to have a handful of spares around in a tech shop to be able to just swap it out and see if that fixes the problem. If you have to know where to look to find these educated guesses, right? But once you've narrowed it down to a specific area, you can literally spend 15 cents, replace 3 or 4 parts, and get to the heart of a matter without actually testing the devices, because the time it takes is, it's more valuable than the 15 cents that you would have spent. Here's another look at the schematic symbol. So again, notice the anode is the negative side, cathode is the positive side. In this particular example, you'll see this is a little bit different from the symbol we saw on the last page. On the last page, the symbol, the arrow was colored in. Again, you just see some variation on this. How does this correlate to the actual device? So here's a picture of most likely a 4001 or 4002 diode. You can see that there's this gray stripe here. Okay, that gray stripe corresponds with this line here. It's very important that this device be put in the right direction. The idea that I've said that this is the negative, this is the positive, right? That, remember that negative and positive are electrical poles, P-O-L-E-S. So that means this is a polarized component. In other words, it does matter which direction you put it in, right? Think about it. If the current's only supposed to flow in one direction, you probably want to install the device in the correct direction to make sure that current can flow where it needs to, and it will be blocked where it's not supposed to go. So it's very important to understand that when you're working with these, you need to make sure to put them in the right direction. Other times, if you don't do that, I've been in situations where I've seen one little tiny 3-cent reversed diode bring an entire device to its knees because it routed electricity in the wrong spot, created a short circuit, blew a fuse, right? And so again, it's not like it's the end of the world, right? But it was one tiny little piece put in backwards, right? That really made things not function. In other cases, you might just lose functionality in a particular part of a piece of equipment, but it is important, right? Now, you will, again, on a schematic, on an actual schematic, you will see the line, you'll see the arrow, so you can kind of understand that. When you're actually working with a circuit board, usually this shape along with a stripe on this end will actually be drawn, or what we call silk screened, onto the board, and you can use that as a guideline for being able to figure out which direction it goes. Sometimes you'll also see a difference in terms of where these actually get soldered. So the holes where these get soldered, the area that actually gets soldered is called the pad. You will find on some devices that on the positive side you'll see a square pad, and on the negative side you'll see a traditional circular pad. So again, that's not a hard and fast rule, but it is something that you do see sometimes. It just depends on the piece of equipment. So that's a traditional diode. Traditional diodes are pretty important. They do a variety of things. They really are kind of a utility piece of equipment, but so it's hard to kind of talk a lot about the specific functions they do, although we will talk about one very important function here in a second. So traditional diode here. Next we talk about the Zener diode. The Zener diode is a little bit different in that it does function somewhat like a traditional diode. However, it's designed with a weakness, and a measurable weakness. It's designed to break down at a predictable and measurable point, a specific voltage. Okay, by the way, this is what they look like. They look a little bit different, but not much. These are tiny components. We're just really zoomed in, right, to really see very nice and close. Um, so in the case of a traditional diode, again, we've got the black body typically with the silver stripe and the silver lettering. With a Zener diode, we typically have kind of an orange core with a clear plastic coating around it and a black stripe to indicate our polarity. And reading the model numbers on these guys is almost impossible. It is extremely small. So it's very important to kind of make sure you keep your parts properly sorted and don't mix them up. But what does a Zener diode do? A Zener diode is designed, again, to break down at a predictable and measurable point. So normal operation on a diode is you allow current to flow in one direction, but if you try to bring it in the other direction, it's not going to get through. Okay, but a Zener diode says, well, wait a minute, right? If there's enough voltage present on that reverse current, then I'll let you through, right? It's almost kind of like a bouncer at a club. That its job is to say, all right, you can only come through if you're on the list, but then there's that one person that slips them, the 50, right, and they let them in, right? If there's enough there to make things work. So what that means is, let's just say that this particular Zener diode is rated at 27 volts, right? That means if the current that's trying to make its way back is at, let's say it's at 14 volts, okay? That's not enough. It's going to be blocked, okay? But if that voltage is 32 volts, then that is above the 27 that was here, so that means it will allow it through. Okay, but what's interesting is because this is rated at 27 volts, what you will find on the back end is not 32, but 27. So it's kind of weird in that regard, right? It basically sets a voltage reference point, maintains that constant voltage as long as the threshold has been reached, right? As long as you've hit the rated voltage for that device, then that rated voltage is now present across the terminals. Now, this is an interesting device here in that this is not something that does a lot of heavy lifting on its own, right? One of the things we're going to see when we look at electronic circuitry is there's typically no one device that does a very crucial job. Most of the time, they are working in concert with other devices to accomplish a particular function. So the Zener diode is really a helper device. A helper device that tells other devices what to do. It's not a very strong or capable device on its own. This is almost like another way to think about the Zener diode is to think about like a warehouse, right? And now I'm using some stereotypical stuff here, so please forgive me for that. But let's just say in this warehouse you have a bunch of really strong, bulky workers down below who are lifting and carrying and forklift driving and doing all the really grunt labor of the warehouse, distributing things around. And then you've got the office manager who, shows up in a shirt and tie every day, doesn't necessarily have a lot of muscle, not really capable of doing much in terms of the logistics in the building, but knows how everything works, knows how to take an order. So we can think of this Zener diode as the manager, right? The manager that really can't do a lot, but this manager can, by allowing that specific voltage through, once it hits a certain threshold, say, oh, hey, we've got an order that's, gone over a certain dollar amount. Now you guys go ahead and jump into action, and it passes this information on to the warehouse workers and says, all right, so now you guys, you got more muscle, you can do more things. Use this information to accomplish something. So that's really the role that we see Zener diodes in. They can be used for other simple things, but that's the primary role they're typically used for. Now notice the schematic symbol here. You're going to see that it's very similar to a traditional diode. You can see here's our traditional diode symbol again, and then here's our Zener diode. Notice the main difference is the flag here. You will sometimes see an additional flag down here. It looks like the letter Z, right? So that's one way that's easy to remember which one is which. And again, they look a little bit different. They're actually typically pretty small. They're smaller than a traditional diode like we've got up here. Both of these devices are pretty small though. Okay, you can tell these little wires here that are coming out of these devices are uh, relatively thin things, and they're magnified to look very huge in these pictures. So keep in mind we're dealing with small stuff. We've got some examples in the classroom. If you want to poke around in the gray parts bin near the front of the class. We also have examples of transformers. We've got a green variac on the shelf. You're welcome to take a look at that stuff as long as you get everything back where it goes. Now, on the same topic of diodes, we've got our traditional diode, we've got our Zener diode. Next, we've got the bridge rectifier. Now, this is an interesting device in that it's not actually a single device. And sometimes it is sold as a single device. In fact, you can see here we've got a picture of a bridge rectifier. This is one box with 4 terminals. Okay, but really what's happening inside here, if you look at the schematic symbols, you have a diode in network with 3 other diodes. Right, so you don't have to buy these devices in a single box like this. You can actually build a bridge rectifier from 4 individual diodes. Now, what do these diodes do? What is the job of the bridge rectifier configuration? The bridge rectifier is a really important device because this is the best way that we know to convert from AC to DC. Now, this doesn't do the entire job. However, it does help quite a bit in that process. So what we have here on the left is we have our AC input. Okay. Now notice when we have this AC input, we've got the positive side here, right? And we've got the negative side here. Now with the positive side, we have a particular polarity, right? We have a positive polarity on our signal, and it is drawn through this diode here, and it's allowed through because of its polarity. And notice it follows the arrow direction here. If it tries to go this direction, it gets blocked by this diode, right? So positive signal comes through here, finds its way out the positive terminal. Okay, the negative signal finds its way over here. And when it comes to this diode, now you would think, well, wait a minute, why isn't it blocked? Well, the reason it's not blocked is because it's the opposite polarity, right? It is actually drawn towards the other side, right? So it allows specific polarities through in specific directions, right? So that negatively charged particle finds its way this way through this diode, ends up on this terminal, finds its way out here, okay? But you'll notice when it comes here, it's going to be blocked because this is the wrong polarity here. Okay, so in this configuration, we see that it is taking AC and routing it the positive to the top, negative to the bottom, right? Now, remember, AC does this, right? It goes positive and then it goes negative, right? So the polarity reverses, right? If we were to reverse this, we would see the opposite polarity on both sides. Okay, so the negative would be drawn through here, would find its way here and find its way out. The positive here would be blocked here, but it would be allowed through here and find its way out here. Okay, so what this allows us to do is it allows us to take our sine wave that was doing this, and now it allows us to turn that sine wave positive, completely takes that signal and makes it unidirectional. Okay, if you remember, our DC signal is supposed to look like this. Nice straight line, right? And we have this to begin with, right, that goes between positive and negative. Okay, so this bridge rectifier is taking all of this stuff here and it is flipping it up, and it's making it all so it's positive. Now, it's not quite a straight line yet, right? And so that's an important observation that we need to make. It's not a straight line. It's not really DC yet, but this is a very important step that gets us there. Now, keep in mind, we can do this, this idea of converting from AC to DC with just a single diode, right? Let's come back to our single diode here. So remember, our single diode allows current to flow in one direction and one direction only. So if we were to run in our sine wave That's a really bad sine wave. My apologies. Let's try that again. If we were to run our sine wave through here, right, what would happen is that diode would allow this stuff through, and it would simply not allow this through on the bottom here. So what we would get is only half of that wave would find its way through. Now, this is rectifying, right? That idea, that word rectifying means that we are putting it in a single direction, right? We're combining it in one direction only, right? So this is what's known as half wave rectification, because we're only rectifying half the wave. The other half just gets discarded. There might be uses for that. Again, if you guys have a really vintage tube guitar amp or a really vintage piece of equipment, the diode that's in there is actually a vacuum tube diode, right? And it is actually doing half wave rectification. It's a very inefficient form of converting from AC to DC, but hey, it's better than nothing, right? This was the original way that it was done, and the bridge rectifier is an improvement on that. But it's very, very inefficient. It's really hard to get a nice stable DC supply that way. But with our bridge rectifier, we are doing full wave rectification, right? Not half wave rectification, but full wave. We're not wasting any of this stuff here. We want to make sure that we get every single chunk of that. And then ultimately what we want is we're going to end up smoothing this out into a nice straight line using some other components as well. Okay, so this is really step number 2 in your traditional power supply. First, we're going to have the transformer, and then that transformer then feeds into your bridge rectifier, right? There might be some other things in there. There might be a little light to indicate that it's on, or we see a fuse before the transformer and things like that, right? But these are kind of the 2 big building blocks in order, right? The transformer, if we look here, right, remember the transformer is going to set us up with the voltages that we need. Here's the stuff from the wall. Here's our 3 different voltages out. And then for each of these 3 voltages, remember, transformers require AC to function. So we've got AC coming in here. We've got AC coming out here, right? So for each of these, though, however, we're going to need to see a bridge rectifier that turns this into DC, right? Each one of these secondaries is going to have a bridge rectifier to make sure that we get that process from converting from AC to DC started. Okay, so keep that in mind. We talk a good bit about the power supply in here because that's a very basic troubleshooting technique, and it's not a very difficult circuit to understand once you understand how all the components work. One of the most common complaints is, my piece of equipment just won't turn on. Well, if it won't turn on, where do you think the problem might be? Right, the problem's going to be in your power supply somewhere, somehow. Sometimes my lights are flickering, right? Oh, okay, well, maybe you've got some failing capacitors in the power supply, right? I mean, it's a very common thing to have to troubleshoot power supplies. So we want to make sure as we go through this semester, we're going to be covering all the details that go into a basic linear power supply. And then if any of you guys need extra credit, by the way, there is an essay that's available at the end of the semester that compares that linear power supply that we cover throughout the semester with what's called a switch mode power supply. That kind of makes things a little bit more compact. There's a little bit more complexity to it, and there are good reasons why we see a lot of them these days. So it's important to understand those as well, but the linear power supply is a little bit simpler to understand. Lastly, before we draw this lecture to a close, let's go ahead and take a look at the LED. So the light emitting diode. Notice in the name, it is a diode. Now, LEDs have gotten a lot of press recently, within the past 5-10 years, and for good reason. They're really cool. Believe it or not, the very first LED that was invented was the red one. And the very last one to be invented was the blue. They all work a little bit differently. They've got different chemical coatings and things like that. But at this point, we have the ability to make some pretty darn good looking LEDs that can light up our houses, light up our stages, light up our film sets, and do a really good job. They're very, very efficient devices. Um, but there are some quirks that come with these, right? So again, let's think. They are diodes, right? They only allow current to flow in one direction. So that means we must make sure that we get them wired up in proper polarity, right? Now, when we look at our leads here, how in the world can we tell which one is positive, which one is negative? So the cathode is the shorter lead. Remember, the cathode is the negative side, right? So it's the shorter lead, but the larger electrode. So let's break that down real quick. So the cathode is the negative side. That's going to be our shorter lead here, right? So this is negative. So it's shorter here, but it's larger inside the LED, right? Whereas the anode is the positive side and is always the smaller electrode inside the LED. So they're kind of backwards from each other in that regard. This pattern down here, though, with the legs is something that's very important to note. And we're going to see this with other polarized components. If they are in this lead configuration where they have the two leads on one side or on one surface, this is called a radial lead configuration. We'll talk more about that when we look at capacitors. If they're in a radial lead configuration and they're polarized, the longer leg is always going to be positive. Now, that's a good rule to know. But what happens if you have a used LED, right? Maybe you are moving it from one place in the circuit to another, or you took it out to do some repairs and now you need to put it back in. If it's been used, guess what? Those legs have already been cut. So how can you tell which one is which? Well, that happens by looking inside, right? If you look inside the LED, you will see that the positive side is the smaller electrode. The negative side is the larger electrode inside the LED. I have seen in my years doing tech work one exception to this. And I couldn't tell you, I don't know what brand or anything, and it didn't have anything to do with anything. It just happened to be that this particular LED I was working with was opposite, and it was really weird. But this is going to be 99.9% of the LEDs you come across, unless you start working with some really weird stuff that I'm unfamiliar with. Okay. If for some reason you're unsure, you can always test it, right? You can use a bench power supply, right? A bench power supply is just a little box where we can dial in whatever voltage we need, have it output that voltage, and we can hook up our LED and we can figure it out, right? However, very, very important. Diodes do not like a lot of current, right? Now, this is a positive thing. This is one of the reasons why LEDs are great for lighting, because they use very little electricity, right? And remember that it's really the flow of electrons that we're actually paying for, right? It's current that we're paying for. Now, of course, on our bill, remember we're looking at kilowatt hours, right? So that is power over time, right? But remember, the main thing is if we don't have any current, right, we don't have any electricity in use. So LEDs and diodes in general don't like a lot of current, okay? So what that means is if we want them to be able to function, we have to put a resistor in series. We have to slow down the amount of current that can get through these devices, or else they will literally burn up. It's not like, stand back, you're going to have a fire. But if you were to fire up an LED without a resistor in series, what you would find is that it would get really, really bright for about 2 or 3 seconds. And then after 5 seconds, I can guarantee you that it will have had this little burst, this little explosion inside, and you'll see some black stuff inside, and that LED will no longer light. It really needs to be limited. Now, how much resistance? Well, that really depends on the LED. You'd have to look at some specifications. Some of them like to be, have something as low as 1 kilo ohm. In some other cases, I've been using resistors as high as 22 kiloohms or even 40 kiloohms, right? It really depends. In general, the higher you go, of course, the lower the current. You'll also find there's a voltage drop, so you will see a slightly dimmer LED that is part of that process as well. So eventually, though, if you keep going up and up and up in resistance, you go so dim that the LED is no longer lit. So there's obviously a limit to being able to do that. Okay. So, oh, and by the way, let me go ahead and recap real quick. I forgot to mention, I believe, that whole resistor thing with the Zener diode as well. I had it on the slide here, right? Usually wired in series with a resistor, but I don't think I mentioned it there. So these guys, again, they can't handle a lot of current, right? The manager of this warehouse gets pretty stressed out if you send it too much, right? So, so you have to wire in a resistor in series. So again, keep in mind, right? These are your connection points on your schematic symbol, and we would also have a resistor connected over here. We haven't covered this schematic symbol yet, but that is effectively what it looks like. So we'd need to make sure we had a resistor wired in series so that any electricity that wanted to pass through that diode had to pass through the resistor first. All right, well, that about wraps us up for today. Thanks for your time, and we will see you guys next time.